I've called my talk "How Far Away Are the Stars," which is a topic that's very near and dear to my heart to be honest. I have this book with me here. This is my first astronomy book I ever had when I was really little, and it's called "How Far Away Are the Stars." So I've been thinking about these questions for a really long time, right? You know, this has really inspired me for a long time. And it's not just me. So this question of how far away are the stars, and how far away is anything in space, for that matter, has really occupied the human race for a really long time, right? For thousands of years. Like even the ancient Greeks, way before Socrates, were really fascinated by these questions. You know, how far away is anything in space? I also really like this topic because it makes a really nice example of like a scientific detective story, right? And it's a really pure example of how great scientific logic and scientific deduction can be, because we work this stuff out starting from small things, and then we get bigger and bigger and bigger, and end up calculating the scale of the entire universe based on just really, really simple observations and common sense. We don't need kind of fancy equipment or anything to work out the scale of the entire universe, pretty much. So it's a really nice kind of pure example of like science at work. It's a really nice scientific detective story. So like I said, so it's not just about the stars, right? So how far away are the stars, what I called it, but it's not just the stars. The general question is, how far away is anything in space, right? Because it's really not obvious. If you see something like the moon or the sun or a cluster of stars, it's really not obvious how far they are away. And you can tell that because you look through all of history and people have had vastly different ideas about how far or how close things are to the Earth. I don't just want to answer the question, right? Because the question, how far away are the stars, has an easy answer, right? It's 2019, you can just go and look it up on Wikipedia and then that star is 10 light years away or something. So the actual answer is easy. What I want to do, what I want to talk about is the question about how humanity has gone about working out how far the stars are away, right? It's this scientific detective story that I mentioned that I want to talk about, like the methods and the way we went about solving these problems. So in particular, we're going to be talking about this thing, the cosmic distance ladder. And so the cosmic distance ladder is the answer to this problem, that distances to anything in space is way too far to measure easily, right? You see a cluster of stars or a galaxy or anything like that, you can't just measure it with a ruler, you can't measure it with any kind of simple thing, right? So we need to be a bit more clever about it. And the way it works is, the reason we call this the distance ladder is that we start small, and you start off with some small observation that you can measure really, really easily, or some small distance, sorry, that you can measure really, really easily. And then you define larger distances in terms of this small distance that you know about. And then you can kind of step up the rungs of the ladder and define larger and larger and larger distances in terms of the stuff that you've already measured. As a way of explaining that, so if you imagine I wanted to measure how wide this lecture room was, I probably don't have a tape measure that's going to stretch the length of this lecture room. So what I could do, I could pace it out. I would measure the lecture room and say, okay, this is kind of 15 paces wide. Then I measure the size of my pace and just do the maths, right? So if I say this lecture room is 15 paces wide and my pace is a meter, we say, okay, it's 15 meters wide. And it's what we've done, we've taken something small, by step that we can measure, and then measured something bigger that we couldn't originally measure in terms of that small thing, right? And so that's basically what we do when we measure things in space. We take something small that we can measure easily, and then we measure bigger and bigger and bigger distances in terms of that small thing. So we'll start off right at the very, very beginning with planet Earth. The question is, how big is the Earth? This has a very, very long history. We actually worked out, by we, I mean the human race, right? The human race worked out how big the Earth was a very, very long time ago. So this goes all the way back to the ancient Greeks, about 2,500 years ago. So they knew the Earth was spherical, right? So apologies for any flat earthers in the audience, but we do live on spherical Earth, right? And interestingly, we've always known this. That's the thing. I think there's this popular myth that we used to think the Earth was flat, right? People will often say, in the Middle Ages they thought the Earth was flat. It's a complete myth. We've always known that the Earth was round. And for 2,500 years now, we've known that the Earth is round. One way of knowing this is that if you can look at lunar eclipses. I don't know if anyone saw the lunar eclipse a few days ago. It was far too early for me. But if anyone sees lunar eclipses, you see that the Earth always makes a round shadow on the moon. Right? You can watch eclipse after eclipse, and the shadow is always round, which tells you the thing that's causing the shadow, the Earth, has to be a sphere. Right? So just from looking at eclipses, the Greeks worked out that the Earth was a sphere. And this guy, Eratosthenes, was the first guy to measure the size of the Earth. And he did it with really, really amazing accuracy, using a really, really simple experiment. It was fantastic. So this guy, Eratosthenes, he lived at home in a place called Syene, and he realized that at a certain time, about midday, the sun was directly overhead. And he knew that because you could look down in a well and see a reflection of the sun at the bottom of a very, very deep well. So he knew the sun was directly overhead and shining down into the well. And then he went on holiday and he went some miles north to a town called Alexandria. And then he realized that exactly the same time of day, right, the same time of day, the sun wasn't overhead because it no longer formed, you no longer saw the reflection in the bottom of the well. And so what he realized is that, by going north from his hometown to Alexandria, he was walking a little bit around the spherical Earth, because he knew the Earth was spherical. And so the first thing he did was to measure this angle, right? So he got a stick and used the shadow of the stick, and he measured the angle that the sun was coming down at 7 degrees, right? Which is 1/50th of a circle, right? That's a 50th part of a full circle. And this is where we had this really great brainwave, right? He had this amazing realization that because he realized that what was happening is that he'd gone a bit round, gone a bit up around the round Earth, and the sun was coming in at an angle. So he realized that if the sun changes by a 50th of a circle when he went north, he must have been walking around a 50th of the circumference of the Earth, right? He must have been walking around a 50th of the Earth. So all he had to do to measure the total size of the Earth was measure the distance between these two towns and multiply by 50, and that would give him the actual size of the Earth. So it's an amazing brainwave. So he did this, so he measured the distance between these two towns, and he quotes this number of 5,000 stadia, which is an amazingly round number. I don't know how much I trust him. A stadium is an ancient Greek unit of measurement, right? It's about 180 meters or something. And so he gives the distance between these two towns as 5,000 stadia. Amazingly round, but there you go. So all you have to do is multiply this by 50, and you get a number for the total way around the Earth, which is 250,000 stadia, right? And then you find your friendly local historian, and you ask what a stadium actually is, and they'll tell you it's about 180 meters, and you multiply this through, and you get this number of about 44,000 kilometers all the way around. And the real answer is about 40,000 kilometers, which is it's astoundingly accurate. You're measuring the size of the Earth down to an accuracy of 10%. Just using a stick, right? So it's like the most primitive piece of equipment. You can get the size of the Earth to an accuracy of 10%. It's fantastic. So now, this is like the bottom rung of our distance ladder, right? And now we can use this to kind of step further and further and further out into space. So the next thing we can answer now using this is how far away is the moon? So this was measured again by an ancient Greek guy called Aristarchus, and he measured the distance of the moon. And he was only able to measure this in terms of the size of the Earth, right? So he couldn't actually get a distance in stadia or in meters or whatever. He got a measurement in terms of how big the Earth is. But we've already calculated how big the Earth is, right? That's how the distance ladder works. We know the bottom rung, we know how big the Earth is. And then from that, we can calculate how far away the moon is. And the way we do this is to use a lunar eclipse. So this is an actual photo of the lunar eclipse as it happened about 4 days ago. So you could have done this. So like I said, I didn't actually see the eclipse, and I know some people in this audience did. If you put your mind to it, and if you had a stopwatch, you could have actually done an experiment to measure how far away the moon is using this eclipse. So all you have to do is measure how long the eclipse takes. And if you do a little bit of maths, that will tell you how far away the moon is. So the way it works is, so this is my kind of cartoon, right? So you have the sun, and the Earth, and the moon, and the sun shines on the Earth and casts a shadow behind it, right? So the sun causes the Earth to have a shadow behind it. Then as the moon orbits around the Earth, when it passes through the shadow, that's what a lunar eclipse is, right? You see an eclipse. And so what you have to do is realise that this shadow is about the same, it's about 2 Earth radii. The shadow is about as wide as the Earth, more or less. It's not quite true, right? Because the shadow kind of tapers to a point, but more or less the shadow is about as wide as the Earth. And then you can say, okay, well a lunar eclipse takes about 3 hours, more or less, right, start to finish. So the moon takes 3 hours to cross this distance, to cross the distance about the width of the Earth at the speed that it's orbiting. So it takes 3 hours to cross this shadow. But we also know it takes 1 month to go all the way around the Earth. That's what a month is, right? It's to find the moon going all the way around the Earth. And so you can do a little bit of maths, which I won't show you, but it's a very, very simple equation, the kind of thing you do in secondary school. And you can use this to work out the distance to the Earth, distance to the Moon, in terms of how big the Earth is. But remember, we've already calculated how big the Earth is, so we know that answer. And you get an answer of about 30 times the diameter of the Earth. And again, that's amazingly accurate. And the modern value is about 30.2 times, like the size of the Earth is the average value. So again, just using kind of just observations and common sense, you can work out how far away the Moon is and almost get exactly the right value. It's really fantastic. Okay, so we can that's the second rung of the distance ladder, right? So we can step up again and say, how far away is the Sun? Okay, and again, this is quite easy to do. We can just use simple geometry as triangles and trigonometry, right? Everyone loves trigonometry, right? So you like a very, very simple thing, and you can work out how far away the Sun is. Again, I won't take you through the full calculation because it's a little bit like doing maths in school. The basic idea is that you have the Moon going around the Earth like this, and if you think about where the different phases of the Moon actually are, right? So you have a full Moon when the Moon is on the far side of the Earth, right? And the sunlight is hitting the Moon slap bang in the face, and so you see a full Moon. And you have a new Moon when the Moon is between the Earth and the Sun, and you have a half Moon in between, right? Except half Moon, if you look, half Moon occurs ever slightly closer to new Moon than full Moon, right? And so all you have to do is measure, like the discrepancy, measure how much closer the new Moon, half Moon happens to the full Moon. Measure how much closer the half Moon happens to the new Moon compared to the full Moon, and that will let you work out how far away the Sun is. Again, I won't take you through the full thing because I don't fancy doing triangle maths for a while, but it's just a basic triangle thing, right? The half Moon happens when the Earth and the Moon and the Sun make a right angle, and then so by measuring how late, if you like, the half Moon is, you can get this angle, which lets you kind of solve the triangle and work out the distance to the Sun in terms of the distance to the Moon. And that's what I just said. Unfortunately, this is slightly where, I've been saying how amazingly accurate Greek astronomy was. This is kind of where the wheels fall off the wagon in terms of the Greeks being amazingly accurate, because what you need to do this is a really, really accurate clock, right? You need to measure how much closer the half Moon is to a full moon, to the new Moon than the full Moon. You're measuring essentially how late the half Moon is, and you need a pretty accurate clock to do that, which the Greeks did not have, right? So Aristarchus, this guy, he estimated that the half Moon happened about 12 hours, kind of before it should have done, like before the halfway point, which would put the Sun about 20 times further away than the Moon. And unfortunately, the real value is about half an hour, so it pushes the Sun 400 times further away than the Moon, right? So yes, the method is completely right, though. The method is just kind of logic and common sense, but unfortunately, not having a clock slightly tripped them up. So nowadays we say the distance to the Sun is this value here, an astronomical unit, which I think lots of you would have seen before, right? This is the standard unit for measuring distances in our solar system. It's a whisker less than about 150 million kilometers. So that's one answer to how far away are the stars, right? The Sun is our nearest star, and it's just slightly less than 150 million kilometers away. Okay, so we want to go a bit further away. Right, and get to our main question, how far away are the stars? To answer how far away are the stars, we can use a technique called parallax. And it's really, really easy to demonstrate how this actually works. It's this thing I'm sure you did this when you were a kid. If you put your finger really close to your face and kind of alternate, like opening and closing one eye then the other, right, you'll notice your finger, it's great seeing you all do this. And you'll notice like your finger kind of jumping backwards and forwards, right? And you play the game, if you hold it really, really close to your face, it jumps a lot. And if you hold it kind of far away from your face, it doesn't jump very much, right? And so the closer it to you, and so that's called parallax, right? What you're doing is you're alternating your viewpoint slightly, and you're seeing something close jump around against the background, and how much it jumps depends on how close it is, right? This is the idea. So your right eye thinks it's here, your left eye thinks it's all the way down here, right? So this is this effect called parallax. And we can do this in space as well. So what we can do, we can shift our viewpoint in space, so just like shifting from your right eye to your left eye, and see something jump around, and use that to work out the distance. Although your eyes are a bit too close together to do this, we have to kind of use slightly bigger scales. And so what we can use is the orbit of the Earth around the Sun. Right, so the Sun is here, the Earth orbits around once every year. So what we have to do, say there's a nearby star here, we take a measurement of a nearby star, and see where it is compared to the distant stars. Then we wait 6 months, and that waiting 6 months is kind of like, opening one eye and closing the other eye. And so we're taking an observation on the other side of the orbit, and then we do the observation again. And this nearby star will appear to kind of jump around, right? And we can use that to measure the distance to the star. And we can only measure it, again, it's like a triangle trigonometry problem, right? We can only measure it, though, in terms of the distance between the Earth and the Sun, which we just measured, right? It's the distance ladder again, we've just worked that out. And so we can now measure the distances to nearby stars in terms of the distance between the Earth and the Sun. This is actually very interesting. So the story jumps forward about 2,000 years at this point. So all of these things I've been talking about so far was about the Greeks measuring things and how wonderful that was. We have to jump forward about 2,000 years now because these parallaxes, the star jumping backwards and forwards, are really, really tiny. They're really, really hard to see. You can't do it with your naked eye. You need a telescope. And in fact, these parallaxes, the closest stars jumping backwards and forwards, like from one 6 month to the next, this wasn't noticed until 1806. And so this was actually used again. This was actually used as an argument against like the heliocentric model. So Copernicus, this whole argument about whether the Sun was in the center of the solar system or the Earth. This was the lack of parallax that people had struggled with until modern telescopes came along, was used as an argument against the idea that the Earth orbited the Sun, right? Because people, the argument went, if the Earth does orbit the Sun, then we should see stars kind of jumping around really, really clearly, unless they're really, really far away. And the idea that the stars were millions of trillions of miles away seemed unreasonable at the time, so the lack of parallax was used as an argument for the Earth being in the center of the solar system. But obviously that, they were wrong on both counts, right? The Earth does orbit the Sun, and the lack of parallax that we see with our eyes, in fact the parallax is tiny, means that these stars are millions of trillions of miles away, right? So with modern methods, so our best way of measuring this, there's a satellite called Gaia, which launched a few years ago, which is surveying 1 billion stars in our galaxy. It measures position with amazing accuracy. This can take us out to a few hundred light years, right? So this is about the closest 10,000 stars or so, which sounds like a lot. A few hundred light years, many millions of trillions of miles. That's really still our cosmic back garden, right? We're not really pushing out into our galaxy at all, if we're only looking a few hundred light years away. So we need something a bit better. We need a way of going further out. And for this we use standard candles. Okay, so the idea behind a standard candle, we need something that we can see that are much further away. And remember, so we can't see things moving anymore. All we have, when we go out further than a few hundred light years, all we can do is just look at the light from something, right, and take pictures, and we have to use that to work out the distance. So what we need is a standard candle, something of known luminosity. Luminosity is like, the intrinsic energy an object kind of shines out into space. We need a standard candle, something of known luminosity. We know how much energy it's putting out. So we can compare that to how bright it looks to us and kind of solve for the distance. And the way this often gets explained is that if you imagine a light bulb, right, imagine it's like a 60-watt light bulb, right? 60 watts is like the intrinsic luminosity, that's how much actual light it's putting out. If you're standing far away from the light bulb, it will look very dim. If you're standing with the light bulb right up in your face, it will look really, really bright, right? It's the same light bulb, it's still putting out 60 watts worth of light, but how far you are away will affect how bright it looks to you, right? And so there's this kind of three-part relationship between how bright the light bulb really is, which is 60 watts, and how bright it looks to you, and how far you are away. And the way this works is, if you know two of these, you can work out the third one, right? So you know how bright the light bulb looks just by looking at it, and if I tell you it's 60 watts, which is how bright it really is, you can work out how far it is away. And so we do the same thing in space. We know how bright a star looks. So what we have to do is know how bright the star really is, and then we can work out how far we are away from the star. So this is the tricky bit, working out how bright the star really, really is, because it's hard to know. It might be a very bright star that's close. It might be a very bright star that's far away, or a very dim star that's close. This is where this standard candles come in, and these are very, very useful stars. These are kinds of stars called variable stars. Right, so some stars are like the Sun the Sun never really changes, it's always the same. There are some stars that are what we call variable stars, that kind of pulsate and get brighter and dimmer over a few weeks. And this lady here, Henrietta Swan Levet, she was one of these pioneering astronomers at Harvard College Observatory. She discovered this really important fact about variable stars, which is how fast they pulse, how fast they get dimmer and brighter depends on this thing we really want to find out, this intrinsic luminosity, how bright they are underneath. And so all you have to do is measure how fast they're pulsing, and this tells you how bright they really are, right? This tells you whether it's like a 60-watt light bulb or a 40-watt light bulb, which is what you want to know. So all you have to do is measure how fast they're pulsing, and that gives you their distance. It's amazing. And so that's the next step of the distance ladder. So yeah, this is an example. This is a Cepheid variable called RS Puppis. It's one of the brightest ones, right? This star varies, and we can look at this and then work out how far it's away because it's pulsating. Incidentally, this is the technique that we use to discover that there is a universe out there at all, right? So prior to our understanding of Cepheid variables, these variable stars, we thought the Milky Way was the only galaxy in the universe, pretty much. Then Edwin Hubble came along and showed that, looking at these pulsating stars, and showed that they had to be millions of light years away. And that has to be outside of our galaxy, right? Our galaxy is 100,000 light years wide, as Monty Python famously said, "You've seen the meaning of life." It's 100,000 light years across. So if you see a star 1,000,000 light years away, it has to be outside of our galaxy, right? So it's these variable stars that we use to show that there is a universe out there at all. Even these, so we can see these variable stars out to about 100 million light years, which again sounds like a kind of stumpingly big distance, but really this is still just like our cosmic backyard, right? Even 100 million light years is kind of peanuts compared to the whole universe. And so what we want is something that we can use at much, much, much larger distances. And luckily we live in an expanding universe. So ever since Hubble came along in the early 1920s, he discovered that the universe itself is getting bigger and bigger and bigger. Right? We live in a universe that's expanding. And we can use this expanding universe to measure distances, right? Because the key feature, the reason Hubble works out that the universe is expanding, is there's this really important relationship between distance and speed. The faster something is traveling away from us, because of the expansion, the further it is away. Right, so if you see something that's going like quite slowly away from you, you know it's pretty close. If you see something that's kind of like whooshing away from you at half the speed of light, you know it has to be really, really distant, right? So all you have to do is measure its speed, and that tells you how far it is away in the expanding universe. So there's this really nice relationship between speed and distance is easy to measure, and speed is easy to measure, and then that gives you distance, which is the thing that we're trying to work out. And again, this connects to the rung lower down on the distance ladder. We understood that we live in an expanding universe. We measured the expanding universe using these standard candles, using these variable stars. So we looked at nearby galaxies full of these variable stars, and we used that to understand how fast the universe is expanding. And we can use this to push to really, really deep distances. This is like the top of the distance ladder, right? We use this to measure the scale of the entire universe. And so what we can do this, we can look at hundreds of thousands of galaxies all over the sky and measure their speeds, measure how fast they're traveling away from us, and this tells you their distance. So then we can make a map of the whole universe consisting of hundreds of thousands of galaxies just from measuring their speeds. And we end up with something like this. And this is, I love this picture. This is a picture from a redshift survey called the 2-degree redshift survey. There's, I can't remember how many, hundreds of thousands of galaxies in here, and every single blue dot is a galaxy. Right? So our Milky Way galaxy is right in here, and every single blue dot here is a galaxy. And if you look at the scale, this outermost edge here is about 2,000 million light years away from our Milky Way, right? So we're a very, very long way. So even I said variable stars are good out to 100 million light years, that's about here, more or less, right? So yeah, so that's why I said it's kind of peanuts compared to the universe. Using redshifts, we can push out much, much, much further than this, but this is a good map of the universe out to about 2,000 million light years. And you can see this is what we call the cosmic web. You can see the universe on the biggest scales has this kind of like foamy sponge-like structure, all these voids and filaments made of galaxies. This is a picture of the universe made in a supercomputer. So this is a picture of the universe on the biggest scales that we've made in a supercomputer that we've tuned really, really finely to match the redshift in that survey, the redshift that I just showed you on the previous slide. So it's our current best picture of what the entire universe really looks like. So all these stuff are galaxies separated by the big voids between the galaxies. And so, this is the reason I like the distance ladder, right? So this is the very top of the distance ladder. We've understood the scale of the entire universe and what the entire universe looks like. And this is the, this is the end point of an unbroken chain of scientific deduction, right? We only know about the size of the universe because we can calibrate it with variable stars. And we only know about how variable stars work because we can calibrate them with parallaxes. And we only know that parallaxes work because that depends on the distance between the Earth and the Sun, which depends on the distance between the Earth and the Moon, which depends on the size of the Earth. So understanding the entire universe is like the end point of a chain that started with just a guy measuring the Sun with a stick, which is kind of amazing. And yes, I'm going to finish there. Thank you.